Good morning, dear students. Welcome to another session of microwave and antenna. So in today's session, we'll be continuing with the antenna discussion. So previously we discussed regarding what are the basic concepts related to antenna, such as directivity, beam width, half power beam width, what is meant by beam area. So these all things we had discussed, what is meant by near field, far field. So few of the concepts we have discussed. So those concepts will be handy in continuation with these discussions that which we'll be discussing in the coming forth sessions. So the first point which we have to discuss in this case is point sources. Now, in order to discuss with respect to point sources, what we have is in the previous this thing, if you remember, we had observed one condition where R should be greater than equal to 2 times L square by lambda. So where R is the distance between the transmitter and the receiver. If I am having a transmitting antenna and a receiving antenna, the distance between those two is R. And based on this condition, the observation point what I am considering, whether it is in the far field or the near field or the Fresnel zone or the Fraunhofer zone. So that will be decided by this condition. If the distance what you have chosen, that is the distance between the transmitter and receiver, what you have chosen satisfies this condition, then the point of observation is in the far field. Generally we are most interested in the far field analysis much than the near field analysis. So it is because you can just observe in previous cases. So in this case, we had observed the field zones, that is the Fresnel zone and the Fraunhofer zone, or it is called as the near field or the far field respectively. And you have an antenna over here, and you are considering an observation point at this location, so which is at a distance r. So now this point of observation what we are considering, say if I might consider just an observation point, or there might be another antenna present here which is capturing the signal which is being transmitted by this antenna. So if that is the case, then this distance r, that is at this point, whether this point falls in the far field or whether it falls in the near field, that is what we have to look out for. So it is based on this condition, that is r should be greater or equal to 2 times L square by lambda. So if this is satisfied, then we consider that the point of observation is in the far field, or what we call as the Fraunhofer region or the zone. Now in this case, L is what? L is the maximum dimension of the antenna. In this case, it will be the length of this dipole. And lambda is the operating wavelength of this antenna. So based on this, we have to see whether the point falls in the near field or the far field. So when we consider this point, right, and we can move around at the constant distance. So if I consider any point here also on the circle, so it is also at a distance r. So if I consider any point over here, it is also at a distance r. So we are assuming at a constant distance r, if I try to measure what the radiation is, so those radiation values will be measured either in the near field or the far field. If the condition is satisfied, that is r is greater than equal to 2 times L square by lambda, then the observation is under far field, and otherwise the observation will be in the near field. Our main interest will generally be in observing the radiation at a distance point, so which satisfies this condition, that is r greater than equal to 2 times L square by lambda. So if it is satisfying this condition, then we are observing the point in far field region. So this is what we had discussed in the previous session. So based on that only, if we continue our discussion, now if we have an antenna over here, it is the same arrangement what we have observed over here. If we have an antenna over here and you're trying to measure what is the radiation at a distance r, what is the radiation at a distance r. So if you're measuring this one, we consider the far field analysis. So in which the r value, that is the distance what we are considering, is satisfying the condition 2 times L square by lambda. Now, since we are observing in the far field, what happens is uh, in the far field, what we can consider is whatever antenna we are observing over here, we can approximate it as a point source. We can approximate it as a point source. So I have, suppose I have a Yagi-Uda antenna, I want to analyze it. So what we assume is, we can assume that this is a point source, and based on that, I am trying to analyze what is happening. So if I try to observe it from a distant point, it will be say like a point source of antenna. So that is what we are considering in this case. So when we observe from a distance point, we assume that the antenna which is under consideration is a point source. Now, how do I take the readings at these point, at a distance r from the antenna? There are two ways. Uh, what we do is, we can have two options in this case. You can keep the transmitting antenna constant. So you have a antenna over here, and you keep this antenna constant, and at a distance r, what you do, you move around this antenna in a circle, that is keeping the distance between this antenna and the observation point constant. So basically what you're doing is, you are just changing the angles. So at different angles, you are trying to measure what is the radiation which is being emitted by the antenna which is under study, and you're trying to measure the radiation at the given points. So this antenna is not disturbed. Suppose if it is a dipole, it will be placed as it is, and what you're doing is, at a distance r and at all possible angles, you are trying to measure, say at 5 degrees what is the value, at 10 degrees what is the value, at 90 degrees what is the value. So this is what you're trying to observe around the antenna. So this is how I can make the observation on the observation circle. So this circle what we are looking is nothing but the observation circle, so on which I am noting down the radiations which are being emitted by this antenna. And this antenna, since we are considering it at the far field, we consider that it will be a point source. So this is one way of measuring the field values or the radiation values on the observation circle. Now what is the other way? What is the other way? The other way is, you keep the observation point constant. So there is say an antenna over here, you keep the observation point constant, say the this distance will be constant, you don't disturb this. Previously what we did, we moved around this antenna, say this is a transmitting antenna, and the observation point we moved around. Now what we'll do is, we'll keep this observation point constant, and we'll rotate this antenna. We'll rotate this antenna. So it is like say if I happen to take, say I have a dipole, and there is a observation point at a distance r. So now what you're doing in this case is, this distance you are maintaining constant. Now this is at say 0 degrees. Now instead of moving this by 5 degrees, what I'll do is, I'll move this antenna by 5 degrees. So in that case, what happens is, so in that case, what happens is, this dipole, I'll rotate it by some amount of degrees. So previously it was along this direction. Now this antenna is along this direction, but what we are doing is we have moved it say around 10 degrees. So what is this information giving? The observation point is constant. You are rotating the antenna and indirectly you are measuring what is the radiation at a distance r when the angle is around 10 degrees. So previously what you had done, you had the antenna constant and you moved the observation point. You moved the observation point. This is at 0 degrees and observation point next time it was here. This was not disturbed. So at 10 degrees, you observed the readings. So the same thing can be obtained even in this arrangement. That is, you keep the observation point constant, you rotate the antenna. You rotate the antenna. So in this way also, you will be covering the entire observation circle. That is, by rotating the antenna, you will be able to identify what are the field distribution or the radiation which is being emitted by this antenna. So this is how we can go ahead with the respect to the observation circle. One is keep the antenna constant, move around the observation circle. One is keep the observation point constant and rotate the antenna which is under consideration. So it is indirectly you are moving the point around the observation circle. So this is with respect to the point sources and how you make the observations in the antenna domain. So next point, what we have to discuss is the power patterns. It is the power patterns. Now, previously we had observed that what is actually meant by a radiation pattern. So radiation pattern is nothing but it's the distribution of either the field pattern or the power pattern or the intensity pattern with respect to the angular variations. That is, you had considered theta and phi. Theta and phi. So keeping the r value constant. Keeping the r value constant. That is, so in this case, you have an antenna and at a distance r you are considering. And whatever values we are observing, we are making the observations by changing the angle. So if I plot it or if I plot the observation of this radiation versus the theta angle or the phi angle, I'll be getting what is known as radiation pattern. Now, when do I classify the radiation pattern as power pattern? In this case, you will be plotting the power which is obtained at different points along this observation circle. So at a distance r, if you're noting the power at this point, if you're noting the power at all the possible angles and you are plotting this values, what you have obtained with respect to the theta or phi, I'll be obtaining what is known as power pattern. So now when I'm plotting this power pattern, right, what I have to observe is I have to check out the coordinate system. The coordinate system will be what? It will be the spherical coordinate system. And we'll be making some observations when we are noting down these things. We assume that the uh, it is a free space in which we are observing these notations and we are plotting them. So when we are doing this, so it is like placing an antenna. Since we have to plot the three-dimensional presentation, right? We can have two-dimensional and three-dimensional. So we can have in power, it will be power pattern. It will be P versus theta or P versus phi. So this will give you the power pattern in two dimension. If I combine both, that is, if I'm able to obtain P versus theta and phi, I'll be getting the three-dimensional. So this is two-dimensional representation. And when I combine both, I'll be getting the three-dimensional representation. So that is what power pattern will be. And when we consider three-dimensional, right, we'll be having r, theta, and phi components. So in that case, we have to consider a sphere. Now, as I mentioned over here, that we consider an observation point which is at a distance r. So this is kept constant. This is kept constant, r is kept constant, and you try to move around. So in two dimensional, you are moving around in a circle with respect to the antenna, and say with respect to theta, and even with respect to phi also, it will be a circle. So when I combine both the circles, I'll be obtaining a sphere. So that sphere will give me the variations. If I am able to identify what is the radiation at those points on the sphere, I'll be able to obtain the radiation pattern in 3 dimension. So in this case, what is done is, at the center, you assume that the antenna is placed. So if you measure the values along phi direction, this will be the condition, that is at a distance r. So you'll not be changing the distance with respect to this. So you'll be considering at a distance r over here, and you'll be making the observations by changing the phi value. Similarly, with respect to theta, what you will be doing, you will be placing the antenna over here, and you will be noting, you will be changing the theta values, and you will be observing. So again, this distance will be kept constant. This distance will be kept constant, and you will be observing along the circle, that is observation circle. So when I combine this and the 5 variations, when I combine both, I'll be having the overall representation in terms of 3 dimensional. So here we assume that there is the antenna, or what we consider, say, the point source at the origin of this coordinate axis, and at a distance r, that is this r is nothing but the radius of the sphere what you're considering. So in previous case, it was radius of this circle. It was the radius of this circle, even in theta or phi direction. Now when I combine both, the radius remains same. So therefore, at a distance point r, when you make the observation over the sphere, you will get the distance will be kept constant, r value will be kept constant, and you will be having a sphere over here. And based on the variations with respect to phi and theta, you will be getting what is the power at this point, what is the power at this point, what is the power at this point, what is the power at this point. So on the sphere, you are trying to measure these things. So it will be, in this form. So this is how the pattern may appear. This is just an example. So this is a 3 dimensional representation of a pattern. So if I take in one dimension, it might be appearing in different forms. So this is just a part of the sphere what you're considering, and you're showing how the variation is happening over here. So you're keeping the distance constant, and you're trying to measure the values of the radiation along this sphere, and you are plotting those values. So if I consider that in 2 dimension, right? So here it will be a little bit clear. So here you can observe that this is actually the 2 dimensional representation. This side also it is the 2 dimensional representation, and from top when I view, this is a 2 dimensional representation. But if I want the overall 3 dimensional representation, I have to combine these. I have to combine these, and I'll be getting, say, the pattern which is seen over here. So this is the 3 dimensional representation. So this again we'll be discussing in the coming forth sessions. So this is with respect to uh, what is meant by power pattern, and how do I obtain the pattern for a given antenna. And when we are mentioning that power, it is nothing but, again, we have different aspects. We sometimes represent it as P, or we sometimes represent it as yes. So this is nothing but indirectly you are plotting what? Power density. You are plotting power density, which is nothing but power flow per unit area. It is the power flow per unit area. So you are plotting the power flow per unit area with respect to theta or with respect to phi, and when I combine both, I'll be getting the three-dimensional representation of the radiation out of the power pattern. Now, in this case, what happens is when we are considering when we consider the far field point, that is here, if I say that this r value what I'm considering is satisfying the condition 2 times L square by W. So what happens is there is one observation you had done where the power density is inversely proportional to 1 by r square. It is inversely proportional to square of the distance. So if you keep on increasing, this goes on decreasing. But this has another point over here. What happens is further as you move further, what happens is this component goes on reducing. This component goes on reducing. So first, just for example, if I say if it is 1 by zero point 0.1, sorry, if it is if it is 1 by 10, I'll be getting zero point 0.1. If I still increase it, say if I make it as 1 by 1000, it will be 10 raised to minus 3. So it keeps on reducing. Say if I take square of this, still it will be reduced. It will be 0.1 square, which will be 0.01. Similarly, this will be 10 raised to minus 6. So you can observe that as we move further, the value of 1 by r square keeps on reducing by large extent. So when we observe that the field values or the power values, what happens is when we go in the far field analysis, the components with 1 by r square. So when we go in the next part of the module wherein we are discussing regarding the field values of the short dipole and the lambda by 2 dipole, so there we'll get to know what are the different fields which are present in the near field and what are different fields which are present in the far field. Generally, when we consider this kind of analysis, what happens is in near field you have E theta, ER, and H phi components. These are the three components which are present, and the other components are zero in the near field. In the far field, what happens is in all these equations, in the near field, I'll be having equations which are having 1 by r, 1 by r square component, and 1 by r cube component. So three components are present. So in all these three equations. So here what happens is when I move further, these two components become negligible. These two components become negligible. So in that case, what we do is we neglect these components and we retain only the components which are with 1 by r. So in that case, what happens is even ER goes off because it has only 1 by r square component and 1 by r cube. It is not having 1 by r component. So because of which ER nearly turns out to be 0, and only component which are left is E theta and H phi. So this again we'll be discussing. So as we move further, what happens is 1 by r square, as the distance keeps on increasing, the power value or 1 by r component value keeps on reducing. So therefore, when we are considering those aspects, right, what happens is the power density, what we are considering, it will be having only the radial component at this point. The power density will be having only the radial component. It will not be having the s theta and s phi component, because we are considering it in the far field. So because of which what happens is we'll be having only the radial component of the power density. So this is with respect to the power pattern. Then along with this, we have to look with another aspect. What is the absolute power pattern, and what is relative power pattern, and what is normalized power pattern. So three components. Say if you're plotting V versus theta or phi. So when do I call this plot? When do I call this plot as absolute power pattern or relative power pattern? or the normalized power pattern. So remember, in power pattern, what we are doing, we are plotting the power density versus theta or phi components. So which will give me the power pattern. And when I'm plotting these things, what happens is, as we have seen that the power density is power flow per unit area. So which will be having the SI units of watt per meter square, which will be having the unit of watt per meter square. If I don't change these values and directly take watt per meter square values and plot it against theta and phi components, theta and phi components. If I take the power density value in terms of say watt per meter square, that is I'm not changing the unit of the say it is in say in terms of watts, and we plot it as theta and phi components with respect to theta and phi components. That plot is called as the absolute power pattern. So in this case, what I'm doing is I'm taking those absolute values and I am plotting the power pattern. So that pattern is termed as absolute power pattern. You are not altering the values, you are noting down the values in its SI unit form and you are plotting it. Now, what is meant by relative power pattern? If you're plotting the say a power density with respect to theta and phi, and in doing so, you are plotting it with respect to one particular direction. Say in this case, say in this direction, I am having a maximum over here. So I take this maximum value, and with respect to this, if I plot all the values, so it is indirectly telling that you are plotting it with respect to theta equal to 0 direction. You're plotting it with respect to theta equal to 0 direction. So if the plot of power or the power density is relative to some angle, over here, we obtain the relative power pattern. Now, this itself can be made as the normalized power pattern. So here, if we consider the maximum value of the power density, so I have the radial component of the power density. Say I'll just represent it as S. So if this one, if I plot it along in any of the directions, with respect to these directions, say I'll be having one particular value over here. So this might be some S1. So if I take S divided by S1 and plot it, I'll get a relative power pattern. Now, if instead of just taking S1, what I'll do is I'll take the maximum possible value of this power density and I'll plot S divided by S1 versus theta and phi. If I plot it with respect to this, then I'll get what is called as normalized power pattern. I'll be obtaining normalized power pattern. So this is what we specify in the case of power patterns. So this is what I have discussed. That is what is relative power pattern, then what is absolute power pattern, and what is normalized pattern. Now in previous sessions also we had discussed regarding power theorem. So power theorem, what it specifies, it gives us the information of the total power which has been radiated by the antenna which is under consideration. So in this case, what is happening? If you know what is the power density, that is power flow per unit area, then I'll be able to estimate what is the total power which is being radiated by the antenna which is under consideration. So I can obtain it with the help of the power theorem. So the power theorem will be stating that the total power radiated by the antenna will be obtained by the surface integral of the power density. The surface integral of the power density. So which is given by this equation over here. So which is P is equal to double integration, which is the closed contour integration, that is the surface integration of S with respect to ds. So this ds is nothing but the elemental surface area. It is the elemental surface area. And in previous session, we had seen what is this ds equal to. So in this case, you can observe This part what we are observing is considered the small elemental surface area on the of the sphere, and through this we are considering the radial component of the power density. So based on that, we have to see what is ds equal to, and we had observed that ds is given by r square sine theta d theta d phi. So this we had observed how we get r square sine theta d theta d phi in the previous session. So from this that session you can just look over and you can see how ds is obtained. So based on that, you have the small elemental surface area is given by r square sine theta d phi. So this ds is nothing but the value what I specified over there, which is r square sine theta d phi. So this is power density specified in terms of power theorem in terms of power density. Power theorem specified in terms of power density, in which this P is the total power which has been radiated, and S which is there since it is having only the radial component. So S is replaced with SR over here. So SR is the radial component of the average Poynting vector, or it is the power density. Then ds is the elemental surface area of the sphere, which is given by r square sine theta d phi. Now in this again we had two conditions, that is if we consider the full sphere and if we consider the half sphere. So remember, what is the range of theta and phi? Generally theta is in the range of 0 to pi and phi is in the range of 0 to 2 pi. If I consider this entire, I'll be having the full sphere consideration. And if I slightly change the value of theta, that is if its value is in the range of 0 to pi by 2, phi remains same. So if this is the case, then I'll be considering half sphere. So this will be useful when you're considering the unidirectional patterns. Unidirectional patterns. So here power theorem gives the definition of how we can obtain the total power radiated by the antenna which is under consideration when you know what is the Poynting vector or the power density. Now, if I apply this equation for isotropic antenna, what will be the total power which will be radiated by the isotropic antenna? So that is what we have to consider. So by definition, what is isotropic antenna? Isotropic antenna or isotropic source is the antenna or the source which radiates equally in all directions. So by this definition, what it implies? So if I just consider this case, so if this is an isotropic antenna, so by definition, it is radiating equally in all directions. So if that is the case, then what happens? If I measure the power value at this point, power or the intensity value at this point, say I am getting some value of SR. Then again, if I change the angle and measure at this point, again it will be SR. If I change the angle and measure it, again it will be SR. So if I keep on measuring on this observation circle, right, I'll be getting same values throughout, whether it is in the theta direction or whether it is in the phi direction, keeping this distance constant. That is the observation point at a distance of r. So if I am able to keep this observation point at constant distance and then measure the values, and if this is isotropic antenna, what happens is all the values will turn out to be same. So this is what an isotropic antenna will be. And practically we don't have antennas which radiate equally in all directions. So isotropic antenna is like a reference kind of thing. So now if I apply power theorem in terms of power density to isotropic antenna, what will be the total power which will be radiated by the antenna? So in this case, let us assume that the isotropic antenna or the source radiates the power density which is SR, that is the radial component which is SR. So as it is the radial component at a distance say r, it will be constant throughout. So this value will be a constant. This value will be a constant. And if I use this value in power theorem, so wherein I have P is equal to, that is the total power which has been radiated by the isotropic antenna which is under consideration, will be the surface integral of this power density into the power density with respect to the surface, elemental surface area. So now since SR is constant, SR is constant, I can take it out from the integration. I can take this SR out of the integration. SR double integration with respect to ds. Now here when I'm considering, say again I substitute the theta values. Theta is in the range of 0 to pi and phi is in the range of 0 to 2 pi. ds. What is ds? ds is ds is given by r square sine theta d theta d phi. So when I simplify this integration is nothing but you are measuring all the points. You are summing all the points on the sphere. You are summing all the points on the sphere in order to obtain the surface area of the sphere. So this is nothing but it will give you the surface area of the sphere, which is actually given by, or the area of the sphere, which will be given by 4 pi r square. So if you simplify this integration, right? If you simplify this integration, you will be ending up with this. So wherein P will be given as SR into 4 pi r square. 4 pi r square. So this will be the value when you consider isotropic antenna. Isotropic antenna. So based on this, I can write the power density as P divided by 4 pi r square. So if you just observe, P is in watts and this is nothing but the area of the sphere. Therefore, it is watt per meter square. So if you just observe, the definition still holds correct over here. So where power density is power flow through per unit area. It is a power flow per unit area. So this is the value what we will obtain for total power when we apply power theorem to the isotropic antenna. Next, we have the radiation intensity. So this is slightly different from the power density. Power density is power flow per unit area, whereas radiation intensity, which is identified as U, is power flow per unit solid angle. So the SI unit of this one would be, if I measure it in SI units, it will be watt per meter square, whereas this one is power flow per unit area. And since per unit solid angle, so solid angles SI unit is what? It is steradians. It is steradians. So therefore, what happens? The unit of radiation intensity will be in terms of watt per steradians. It will be watt per steradians. So now, how do I apply power theorem in terms of radiation intensity? So there is slight change what we obtain. So the definition remains the same, power theorem. So here we had power theorem in terms of the power density. Now we have to define power theorem in terms of radiation intensity. So again, power theorem uh, gives you what? Power theorem gives you the total power which has been radiated by the antenna under consideration, and it is obtained by the double integration of the radiation intensity with respect to the solid angle d omega. Here it was s into ds, but this will be u with respect to d omega. So this was with respect to surface, this thing. Here also it will be with respect to surface itself, but you have to consider the solid angle representation. So when I apply that power theorem, what happens is, with respect to radiation intensity, slight change will be we can observe. That is, it is double integration of, I'll consider that it is u naught, because as per definition of isotropic antenna, if I apply the power theorem for isotropic antenna considering the radiation intensity, what we'll have is, we'll have If I consider the isotropic antenna and I measure the radiation intensity at a distance r, I'll be seeing that all the values of radiation intensity on this circle, observation circle, will be same. And if I consider that it is u naught, it is u naught. So then in that case, this equation will be u naught into d omega, d omega. Now what is d omega? You had seen that it is r square sine theta d theta d phi. So this we had written as r square d omega. So this part what is there is nothing but d omega. So wherein d omega is sine theta, d theta and d phi. So in this equation, what we do is we substitute d omega with sine theta, d theta, d phi. So when we do that and take the integration, again u naught is common, u naught is constant. So I take it outside the integration and I take the integration of d omega. So when I substitute this equation, right, when I take this representation, so in this case, r square will not be there. It will be sine theta d phi. Since I am just integrating d omega, it will be theta is equal to 0 to pi and phi is equal to 0 to 2 pi. So when I integrate it, I'll be getting phi as 2 pi and theta, when I simplify it, I'll be getting it around 2. I'll be getting it around 2. That is this value. I'll be getting only this parameter. R square will not be there. R square will not be there. So I'll be ending up with what equation? I'll be ending up with P is equal to U naught into 4 pi. U naught into 4 pi. So this is the equation what we get for the total power which is being radiated by the antenna under consideration when you are using the radiation intensity. So it is P is equal to 4 pi U naught. And in this case, right, U naught which is there, it is generally considered for say simplified purposes that it is the average radiation intensity which is being emitted by the antenna which is under consideration. It is just an assumption in order to identify what is the directivity of a given antenna. So here we have two equations. So one is total power in terms of radiation intensity, which is SR into 4 pi R square, and total power in terms of radiation intensity. This is power density. And in this case, it is the radiation intensity, which is 4 pi into U naught. So this is with respect to power theorem in terms of power density and power theorem in terms of radiation intensity. So, and again, when we are speaking of radiation intensity, we can plot radiation intensity against theta and radiation intensity against phi. So this one will give me the intensity pattern. It will be giving me the intensity pattern, or sometimes also we term it as the power pattern. So this will be giving me two-dimensional representation. If I plot U versus theta and phi together, I'll be getting three-dimensional radiation pattern or intensity pattern. So again, if I consider U in watt per steradian and plot it with respect to theta or phi, I'll be getting the absolute radiation pattern or the absolute power pattern. And if I plot this with respect to some specific direction, say U1. If I plot U with respect to U1, I'll be getting the relative power pattern. I'll be getting the relative power pattern. And if this one, if I consider as the maximum radiation intensity, I'll be getting the normalized power pattern or normalized intensity pattern. So this is all for today. I'll be continuing in the next session. Thank you.